Hi everyone, welcome to the second video of this series in which we are discussing about the designing of a search autocomplete system design. So in the previous video we have discussed about the two main features in a high level details, like one is the data gathering service, which also has the frequency table, and the second which was the query service, which was used to retrieve the autocomplete suggestions. And for that we saw that by using the frequency table we used a SQL query to gather the top 5 suggestions for a particular input. However, it seems that using a SQL query for a small dataset might work well, but for a large dataset it would lead to some bottleneck in performance. So in order to work around against this bottleneck, we will be diving deep into the implementation of certain data structures and how data is being retrieved from those data structures very efficiently to suggest the autocomplete suggestions to the particular user depending on the input. So we will be diving deep into the details of its implementations. So without any further ado, let's dive deep into the details of those implementations. So now let's discuss about or dive deep into the details of these implementations of what we discussed about the problem and its solution. So for that we will be introducing our first topic and the data structure which we use to retrieve the autocomplete suggestions or store the autocomplete suggestions, and that is a trie data structure. So a trie data structure, I'll be not diving deep into the details of its implementation. I will be posting a link in the description. You can read about it, but in high level details I'll explain what it is. It is like a tree-like data structure. So a tree has nodes and edges, so it also has node. So each node has two things. One is a marker, or a flag, you can say, is end of word, denoting whether that node is a end of word or not, and it's a boolean value, let's say true or false. And it also has pointers to this particular node, since each node has, and we are dealing with English characters, so it will have 26 characters of 26 numbers of arrays of node. So it's like we have from denoting A to Z. So suppose a particular character comes, so we type A, so it will check whether this node is empty or not. If it is, means basically pointing to a null or not, since there is no entry of A, so it will mark it as 0, or some A is being now inserted into this node, so something it will be mark it with it something, and then it will check whether this is the end of word or not. Then basically A is not usually an end of word, so this will be marked false. And from here we will be creating another empty node. Empty node, what do I mean by empty node? Basically another node structure which has all the parameters of this node inbuilt here, and this is basically all the values are pointing to null, since there has no other word being introduced or no other letter being introduced. So like let's say when I put an n, so I am at this node currently, so this n here will be marked, right? And again a node will be created and this will be marked as an empty node, and this is a leaf node currently. So like let's say this is my, again I have a character being introduced, let's say T. So for that T will be marked here, let's say, and this is also my end of word. So what we'll do is I'll go to another node, I'll create another node, or I can put here also my flag of is end of word as true, and thus it becomes a leaf node, and instead of not introducing another node. So like this we can build a trie data structure. So this arrows you can see, they store like A, N and T, right? So this is A, this is N and this is T. So this N total denotes a AND word. Okay, so like this we build a trie data structure. So let's see now how this trie data structure is being implemented in our designing of autocomplete suggestions. So for that I'll take an example of a pre-built trie data structure to cite an example, and also we'll be discussing about that. So here as you can see we have a trie data structure, and the corresponding frequency table which we discussed in the data gathering service is also being built. So storing only the information of the words. So like here you can see this is a tree word which is at the leaf node, true, try, toy, and all these words are being stored in a try format. So like t, tr, t, r, e, just like we saw the ant example. So words are being stored here in a try data structure, and also a corresponding frequency table is being built whenever this words has been searched, etc. So only storing the words in the try data structure is not sufficient. We also need to store the frequency of those words in the try data structure, which will help us in order to suggest the top 5 autocomplete suggestions for our searched word or searched prefix. So after we incorporate these frequencies into our try data structure, so it will look like for tree it's 10, for true it's 35, for try it's like 29, for toy if you see it's 14, for wish we have 25, and for win we have 50. So now we have incorporated this frequency. So how does this autocomplete work with try right now, right? So for this we will define some terms, like let's say P is denoted for prefix length. What is the prefix length? Prefix length is basically the number of characters which we have typed for a particular word. So like for TREE we have typed TRE, so that is the prefix length of 3. So N, let's say, it denotes number of nodes in try, so total number of nodes in the try, and we have C, which is number of child of a given node. Okay, so we have these terms. So now what is our goal? We have to find the top. So what is our goal? Find the top k most searched queries, right? Depending on our input. So let's say I type tr. So for that, if I see from this frequency table, what should be suggested to us is like it's tr. So true will come first, right? True will come since it has the frequency of 35. Then try should come, frequency of 29, and then tree should come since it has a frequency of 10. So sorted in non-increasing order. So how do we retrieve this in a faster method? This was like manual, we checked up and we got these suggestions. So how do we retrieve this using the try? So for that we have we find the prefix, right? So like we have typed tr, so I'll go here t, then I'll go here tr. Now I am at this node. From here I will traverse to all the child up till the leaf node. So how number of child? So I will traverse all the child till the leaf node. So I will go here tre, I will go here true, I will go till here. Okay, so find the prefix. So prefix length is p, so finding till going there it will be of order p. Then traverse from this prefix all its child till the leaf node, right? So that is a time complexity of order c, and from that we have to get the top k suggestions. So for that we will have total 3 children. So total here 3 children, so total 3 words we will be getting as our suggestions. And if we sort them, so first like we saw here, after sorting in non increasing order, so it became true, then try, then tree. So sorting also takes order, let's say c log c complexity. So total time complexity what will take is order p and order c for the traversal of the children, and then sorting and giving the top k suggestions. So this is the entire time complexity which will be requiring. So this we have seen with the help of an example also how we are getting this, right? So this is understood. So can we just improve or optimize the performance of this thing? So can you think of something like, instead of traversing to all the children till the leaf node, getting all the words, sorting them, what if we have this information available already here at this node, right? Of all the information, like tree is of 10 here, true is 35, try is 29. All these informations are available at this node only. Then we don't need to travel all the children. We can get the information from here, sort them, sort the input, sort the information which we have got, and then suggest the top k suggestions for the typed input, right? So this is something which will be optimizing in our approach. Okay, so firstly, it's like one approach is like which we discussed is caching the search queries at each node. Second thing, what also we can see, like the prefix length in most of the cases might not exceed a large number. So let's say it can be a constant number up to, let's say, 50 length. So thus it becomes, if you see, order p becomes to some constant. So order of 50, which is a approximately we can say order 1 constant time. So thus it also reduces the time complexity. So these two optimizations we can include in our designing to retrieve the suggestions much faster, instead of traversing the entire try node, getting the words and then suggesting the words. So this is one of the suggestions which we can look into. So this was the first topic. So let's now look into how data gathering is being done. So this is, we saw like the try is already present, already built, and then frequency table is also present, and from that we are gathering the suggestions. So how this try is actually being built from the data we put into the search option, how this data is being fed into the try, how are they stored in the database, and how this frequency table is being generated. Now we will be looking into this in the section data gathering service. So we have this data. Every time a user types a query or searches something in the search menu, this data is being fed into the frequency table and they are being stored, right? But in order to perform auto suggestions to that particular search query, we need to gather this data, perform some operations on that data, like build a try and then suggest him. So how frequently should we be doing this operation? So like it depends on the use case and depends on the app which we are using. Some news application or some applications like Twitter, where data is being rapidly changing, the method of updating the gathered information, updating the try is much faster than some search operations in like Google search or something like that, where the data is not being updated much faster. So for that, depending on our use case, we can design the frequency of building the try. So let's understand this with the help of a flow diagram of how things are being done actually. So with the help of this flow diagram, we will be understanding how a data gathering service actually works. So this is first thing is like the analytics log. So analytics logs is nothing but anything which we type in the search query, it's being appended into as a log without any indexing. So like for suppose at timestamp t1, someone types tree, at timestamp t2 someone types ant, at timestamp t3 again someone types tree. That tree will be appended after this ant along with the timestamp. So this is analytics log. So it's like two fields like the word and the timestamp, and they are without any indexing, they are appended to the logs. So it might look like a table like we have seen in the frequency table without any frequency, just a normal word and timestamp columns present there. So after that we will be having an aggregators. So the size of the analytics logs is usually very large, right? Since there is no indexing, each and every word we type, be it repetitive, it is being appended into the logs, and data is also not in the right format, right? So depending on your use case, like we mentioned about whether it's a real-time application where data needs to be updated very frequently, or some application where data can be updated after a certain period of time with some loose threshold, etc. So for that, what we use, depending on our use case, we aggregate our data differently. So what do we mean by aggregation of data? So aggregation of data is like these aggregators, what they do perform is they, suppose we update in a weekly manner, right? So and in our analytics log, our data is stored like this. So I have tree here, it at timestamp at let's say 1 2 3. Suppose this is an imaginary number, not a real timestamp. I have end here at timestamp, and date is like 1st of Feb, and here this is let's say 1 2 3, this is 3rd of Feb, right? Again tree here, let's say this is 8th of Feb, right? So aggregated data, what it will do, if you see, for tree it will be 1 for 1st of Feb, again for tree it will be 1 for 8th of Feb. So we are actually, for a weekly basis, we are aggregating our data from the analytics logs and building our aggregated data. So it will look something like this. The aggregated data will look in a 1 week time, since the tree word has been searched one time, so it will look like this. Tree is 1 in from 1st of Feb, on 8th of Feb after a week, that is also, there is one tree which has been searched. Okay, so I'll be showing you a table by which you can also gain an idea how it actually looks in a real world scenario. So this is basically an aggregated data. So as you can see, tree has a frequency of 12,000 on 1st of October 2019. Again after a week it has a frequency of 15,000. So in this period 15,000 times tree has been searched, or someone has typed tree in the search query. Okay, so like this, there is also toy and there is also tree entry, etc. So you can understand how an aggregated data works or looks like. And now we have these workers. So what does this worker do? They perform a synchronous job at a regular interval, like a cron job is being run, which updates weekly the trie database. Basically it builds the trie, updates it into the database and also in the cache for faster retrieval. So trie cache is basically, so this is trie cache. So trie cache is basically a distributed cache system, you can say, for faster, like in memory, this is, as it's a cache for faster read and write, for faster read operations. So and there lies the trie database, which acts like a persistent storage. So how this trie database will actually look? So what is this trie database? It can be in two forms. One is like a document store. So like document store, it can store like this is particular node, let's say it has A. From A we have child, let's say node N, like for the AND, node P if I have an apple or something board like that, and all those information, and also the is end of word or not flag. So like this, in a serialized data we can store this in a document store. So for document store, popular document stores are like MongoDB, which is a good fit for serialized data. So what does worker do? Worker takes a weekly snapshot of this newly built trie, serializes the data and stored it into this document store. Another thing which we can use is also a key value store. So if you want to know more about the key value store, its implementation in details, you can see my video. I'll post the link in the description box. So of designing a key value store. So a trie can be represented in the form of a hash table. So that is a basic form of a key value store, a hash table. So how is trie being mapped into a hash table? For that, what is the key? So key is basically the prefix in trie. So like you saw, like the tree R, TRE, TRE, these are basically the keys of our hash table, and the values are basically the associated values of this trie node, basically, or is it end of word or not, or how many. So like this is TR, what if it was TO, like that. So how many children it has, and where it spans to, whether it is end of word or not. All the basic metadata is being stored as the value of this hash table. So if I look into key value store, how it looks like, along with the try, mapping with the try. So I'll show you with an example here. So this is an example of a try. So like the word best is there, bear is there, and each try has cached the information of, each node has cached the information of the words which are being present in the child and also their frequency. So like you can see, this B has been mapped as a key to this hash table, and all this corresponding metadata like the words which are being formed in the child of it along with the frequency are also stored as a value. So now after the data has been gathered, how it is stored in the database, how it is stored into the cache, we have discussed all these details. Now let's look into how we retrieve those data. So for that we will be looking into our third part, that is the query service. So query service is simple. So like let's say we are trying to fetch top 5 results for autocomplete suggestions. So for this we'll also understand with the help of an flow diagram which will make us easy to understand. So here we'll understand this query service with the help of flow diagram. So like user like types tr in the search menu. So let's say user types tr in the search menu. So the request goes to the particular server handling this auto search completion through a load balancer. It then fetches the suggestions from the cache. If the data is not being present in the cache, then it sends a request to the database. Database updates the cache and ultimately returns the top 5 suggestions to the server, and server in turn returns the suggestions to the user. So in this way query service happens. So this is very easy to understand. So one thing we will be looking into or discussing in a high level, like since on typing of each character, let's say TRE, every time the suggestions change, right? So after TR there can be TRAM or TRO, J and Trojan, etc. Like that you can understand. So once we type TRE, all these are invalidated, and now we have let's say TREE and other suggestions. So one thing you will notice that although every time a query is being sent to the backend to get the suggestions for every character which we type, the browser is not being refreshed. So why does this happen? So for what request actually goes to the backend is the AJAX request. So you can read more about this AJAX request, how it occurs, so that there is no browser refresh every time a request is being sent to the backend. So I'll post the link in the description, you can read about it. Another thing which we can do is for faster retrieval of the suggestions and not sending every time the request to the backend is like browser caching. Depending on your use case though, let's say your use case is like you're using an application like Twitter where data is being evolved every time, or data is being replenished and new data is being fetched every time. So for that you have to send the request to the backend in order to get the autocomplete suggestions. But in suppose you're using a Google search where the suggestions are not changing in some small period of time, you can do a browser cache, and let's say like 3600 or 1 hour for 1 hour, and this will improve the performance very much, right? Very much fast. So we'll get directly from the browser cache. So this is like how a query service happens using AJAX request, no browser refreshing, also from browser cache for faster retrieval. Well, next section we will be discussing about some try operations. So try operations is like, one is the create. Try is created basically from, if you remember, we have discussed in the flow diagram, try is basically created from the workers using that aggregated data. If you remember, if you see the flow diagram which we discussed here, the workers create the try from this aggregated data. Okay, so let's say now we have to update the try, like new words have come, new suggestions have to be fetched, which is also frequent, right? So there are two ways you can update this try. One is update try weekly. So after a week we create a new try, and that new try replenishes or replaces the old try. Second is we update the try node directly. So we mostly try to avoid this because this is a slow operation. Although if the size of the try is small, it is acceptable, but when the try is very large, once we update a try node directly, all its ancestors have to be updated, all the frequency, values have to be updated, and that is a very resource intensive and heavy operation, so we mostly try to avoid this. And the third operation which we do is delete. So like some hateful content, some explicit contents which are not good or not favorable for the particular user to be shown as a suggestion, what we do is, before sending the data to the user, sending back the suggestion to the user, what we do is we apply a filter layer before the, let's say that this is the try cache which is sending the suggestions. We apply a filter layer which checks whether these suggestions can be given to the user, and then send the request to the user through the API servers. So these are the try operations which we perform or which we support in our design. And the final thing which we will be discussing is scaling, which is so since our English is only supported language, we can shard the database based on the characters. So let's say my words are starting with A, my words are starting with B, we can shard them based on the first character. So we will have 26 servers where the data will be sharded, the try will be sharded and distributed. But if we need more than 26 number of servers, what we can do? For that, we can go to the second level, like AA to A's G in one server. So like this is one server. From here again we distribute, right? AA to AJ, AK to AS, AT to AZ. Like this we distribute them. And like that we can partition our data into multiple, or shard our data into multiple distributed servers, and handle thereby making the resources more faster operation, and thereby scaling our database, like, right? And also one thing which we need to keep in mind is like unequal distribution of data. So like the number of words starting with A is like, let's say 3000, whereas the number of words starting with S to Z in total is 500. So if we shard on the basis of the first character of each word, what will happen is like shard 1, which had all the words starting with A, will have 3000 entries, whereas shard S will have, let's say 20 to let's say 100 entries, and like that, which is much less than the shard 1, right? So this is an unequal distribution of data. For this, what we can do is we can include other characters. Let's say from J to Z, there are total 3000. So put all the words which are starting from J to Z into one shard, and another shard will contain this. So shard 2 will have all the characters or the words starting with J to Z, and shard 1 will have all the words starting with character A. So in this way for this we will have a shard map manager which will handle this distribution, and it acts like a lookup database for identifying where rows should be stored. So in this way we can scale our system, and we have a highly scalable system, or distribute the try databases across multiple data centers or multiple databases. So with this we come to the end of this designing of a search autocomplete system. Although there are multiple questions which might be asked, or which we can ponder over at the end of the interview, with having a discussion with the interviewer. Like some questions which we might ask is like, how do we support multiple languages, or what if the top search queries varies from country to country, or how can we support the real-time search queries, right, with some applications which are, when a certain particular event is happening or some breaking news happened, how can we update in real time? So we can have a good discussion with the interviewer at the end of this system design round interview. So with this we come to the end of this designing of search autocomplete suggestion. So thank you for watching this video, and stay tuned for more such interesting videos on system design.